Okay, and so today we continue in chapter 5. And here we are talking still about probability, okay? And I left off talking about mutually exclusive events, okay? And so now we're going to talk about conditional probabilities. And so conditional probabilities, we express this as the probability of A given some other event B. Okay, so we will say, the probability of A given some other event B. Okay, and this is written as probability of A vertical bar B, and essentially this means, this is the probability that A will happen if we know, or if it is given if we know B has happened. Okay, and so this is what we have here. And so an example of this could be, imagine being at an airport. Okay, and so in Los Angeles we have pretty good weather, but let's say you're in Chicago or something like that. In January or February, okay? Being at an airport, let's say Chicago in January, and we could say, if there is a storm, then the probability that our flight is delayed, or our flight will be delayed, is, I don't know, I'm going to just make up a number and say 0.7, okay? And so the way we would write this is basically, the probability of a delay, if we know that there's a storm, is 0.7. So we would say the probability of a delay given storm is equal to 0.7. Okay. I just want to make sure everyone's okay with going from the sentence to having it written in our kind of symbolic fashion. Okay. On the other hand, if we say if there is no storm, then the probability that our flight is delayed is only 0.1, okay? So we'll say, if there is no storm, our flight can still end up being delayed for one reason or another, but the probability that it's delayed is only 0.1. So how would I write this? Probability of, or what would I write here? Delay, vertical bar, no storm. It's 0.1, okay? So notice that, these two numbers, they don't have to add up to 1, okay? On the other hand, okay, I could say if there is a storm, then the probability our flight is on time or is not delayed would be what? So here we have probability of delay given storm is 0.7. Okay, let me just save this. This is week 4, Wednesday. Okay, so over here we said probability of a delay given a storm is equal to 0.7. What is the probability that there is no delay given that there's a storm? This is going to be 0.3. So these two things have to add to 1, okay? So these must, so probability of A given B plus probability of not A given B must add up to 1, okay? Okay, but there's nothing about A given B versus A given not B, okay? But probability of A given B versus probability of A given not B, there's no relation, okay? All right, and so that was, you know, probability of delay given no storm has no relation to probability of a delay given a storm. Okay. What does this signify? So we would say probability of storm given delay. What does this mean? Okay, so if we know the weather, we can kind of try to predict whether our flight will be delayed or not. Okay, over here, the scenario that corresponds to this would be, you know, imagine you're the friend who's picking someone up from the airport. Okay, and you check the arrivals, and it says flight has been delayed. Okay, and let's say you're not going to check the weather on your phone. Okay, so you look at the board that says arrivals. And it says, flight 321 delay. Okay? So now, so we know that there's been a delay. Okay? And now you're asking, oh, I wonder if my friend got stuck in a storm. Okay? I wonder if there was a storm. Okay, and that's effectively what we're saying here. Okay, so if we know there was a delay, what is the probability that there was a storm? Okay, so this is probability of a storm given that we know there was a delay. Okay, so it's very important that we can differentiate between delay given storm versus storm given delay. Okay, they look similar, they even sound a little similar, but they are distinctly different. Okay, so we can do like a little example here. Okay, so let's say I don't know, we surveyed some people, and we ask, do you watch baseball on TV? Okay, and they can answer yes or no. And then the next question will be, do you attend baseball games? Okay, and the answer there could also be yes or no. Okay, and so maybe we asked a bunch of people. So let's say I asked a total of 300 people. So we'll say TV versus no TV. And we'll say games versus no games. Okay, and this being, you know, baseball TV and baseball games and things like that. I'm just kind of shortening it up. Okay, so out of 300 people, how many do you think watch baseball on TV? I don't know. I'm just making up numbers here, okay? So don't hold me to this. We'll say 90, okay? Which means over here we have 210. And then out of 300, how many go to baseball games? Maybe we'll say 60. This leaves 240, okay? Out of the 60 who go to games, how many watch TV? I don't know, I'm gonna just make up some stuff here. So here I have what, 36 and 204, is that, did I do my math correctly? Okay, I think I did. Okay, and so over here I can ask questions like, what's the probability that someone watches baseball on TV? Okay, and what's the probability that someone attends baseball games? Okay, and so our answer to the TV would be what? If I pick someone at random out of here, we would say 90 divided by 300. And I get 0.3. I think you guys get this, but then I'm also just, let me just see like a smile and a head nod or something here. Okay, so are we good with this, 0.3 here? Okay, and then games, we would say what? 60 out of 300, 0.2. Okay, I mean we can verify this. Okay, all right. Okay, your answer choices here. Clicker question. Okay, so I will pick someone at random. Okay, all right, so your answer choices will be 0.18, 0.6, 0.9, 0.3, and 0.2. Okay, so question one, let me get this clicker software started. Let me just make sure. Yeah, okay. Okay, so I'm going to pick someone at random. What is the probability this person watches baseball on TV and attends baseball games? Okay, so go ahead Clickety click. So you can talk with your neighbors. What's the probability? So we're picking someone at random. What's the probability this person watches baseball on TV and attends baseball games? Okay, we'll say 5 more seconds to get your clicks in. 4, 3, 2, 1, and stop. Okay, and the answer is indeed answer choice A. Okay. So this is, we would say, probability of TV and games. And we get 0.18, okay, or 54 out of 300, 0.18, okay? Let's see, how should I do this? I'll save this and I'll copy everything, make a new slide, and then so this next question, so I'm gonna chop this out. Okay. All right. So the question now is, I will pick someone at random. Okay. The person I've selected attends baseball games. Okay, and the question now is, what is the probability this person, this selected person, also watches baseball on TV? Okay, and so we'll have it fire up there. Okay, 5 seconds. 4, 3, 2, 1. Stop. All right. Let's see. Indeed, that is the correct answer. Answer choice C. All right, and so symbolically, this question corresponds to probability of, what do I put here? Probability of TV given games. Okay, and we would say basically there are 54 people who watch TV and games out of the 60 people who watch or who attend games, and this is 0.9. Okay. All right, and I'm not going to bother making a clicker question out of this, but we should have also probability of, so we had TV given games. What is games given TV? I would put in the numerator 54, but in the denominator I would have 90. So I would have 0.6, okay? So probability of games given TV is 0.6, probability of TV given games is 0.9, and probability of TV and games is 0.18, okay? So these, the questions that ask these are all kind of similar sounding, but they are also different, okay? And so, so make sure we can differentiate between these. If I say, what is the probability that a TV watcher attends games? Which one does this correspond to? 0.6, 0.9, or 0.18? 0.6, right? This one is 0.6. This is probability of games given TV, okay? So, so all of these, they do sound kind of similar, but they are distinctly different. Okay, so the general formula is probability of A given B is going to be the probability of A and B divided by the probability of B, okay? Now when we had the table, we kind of skipped over one of the steps, but if we did probability of games given TV, the probability on the top would be probability of games and TV divided by probability of TV. Games and TV we found to be 0.18, and probability of TV we found to be 0.3, and so here we would get 0.6, okay? Or this was 54 out of 300 divided by 90 out of 300, which simplifies to 54 out of 90, also 0.6, okay? So however you do it, it's going to work out, okay? So probability of A given B is this. Likewise, probability of B given A will be in the numerator, probability of A and B, and in the denominator we would put probability of A. Okay? Maybe it's worth noting that probability of A and B is the same thing as probability of B and A. So, so here we're just kind of flipping the letters around, and this is kind of the general form of a conditional probability. Okay. When talking about conditional probabilities, we inevitably talk about two events being independent, okay? Well, okay, before I go on into independence, I just want to make sure we're all good here? We're all good here? Okay. Okay, so two events, A and B, are independent if the outcome of one event has no influence on the outcome of the other event. Okay, so we can say, you know, 2 coin flips, or even, you know, flipping a coin and rolling a die, those are independent, okay? So 2 coin flips are independent of each other. Okay, or you know, rolling dice and flipping coins are also independent. Okay, when you flip a coin, it has no influence on future coin flips. When you roll a die, it's going to have no influence on the coin flip, or vice versa. Flipping the coin will have no influence on the outcome of rolling a die. On the other hand, the storm and the flight delay are not independent, okay? Okay, the presence of a storm increases the probability of a delay. Okay, or the absence of a storm decreases the probability of a delay. We can also say that. Okay, and even vice versa, you could say the fact that there was a delay increases the kind of the likelihood that there was a storm, or I'll say changes the likelihood or probability that there was a storm. Okay, so this concept of you know, the outcome of one influencing the other, it's not necessarily a cause and effect type of thing. It's just that when we know the outcome of one of these events, the probability of the other event changes. So it would be silly to think that delays at the airplane or at the airport would cause storms in the sky. It would be silly to think that. However, you know, if we're just talking about, oh, was the flight delayed? They probably had a storm or something like that, okay? The knowledge of one outcome influences kind of the probability of the other event, okay? And so those would be events that are considered dependent, or you can just say not independent. Okay, so mathematically, what does this mean? Okay, so if A and B are independent, okay, then think this through. What is the probability of A happening if we know B happened? So in other words, the probability of A given B would be equal to what? So A and B are independent, meaning the outcome of one has no influence on the other. So what is the probability of A happening if we know B has happened? I could make a hard clicker question out of this, but I'll be nice to you guys. Okay, it's not 0. It's not 1. It's not 50%. It is the probability of A. It's the probability of A. Okay? The probability of A happening, if we know that B has happened, is still just the probability of A. Okay? So the probability of A, whether or not B has happened, is just the probability of A. So, likewise, probability of A given not B is still just the probability of A. Okay, and so we can use this knowledge to ask, are events A and B independent? Okay, and to check this, we just see if probability of A given B is equal to the probability of A, okay? And if this statement is true, then A and B are independent, okay? Does that make sense? Okay, so let's just do a simple example here. If I can flip to the next slide. So this is a silly example because we already know the answer to this question is that they are independent. So I'll say, is wearing glasses independent of being left-handed? Okay, and we know that the answer to this is yes, right? Or I mean, that we have no reason to believe that wearing glasses is linked somehow to being left-handed. Okay, if the question was, is being a baseball pitcher independent of being left-handed? The answer there is no, okay? It's like, as far as occupations go, if you're left-handed, like there's more left-handed people who are baseball pitchers because they can throw curves the other way for right-handed, whatever. Anyway, okay, so we got, so we will say left versus not left, and this includes everybody who is not left-handed, whether you're right-handed or ambidextrous or whatever. If you're not left-handed, you're not left-handed, okay? And then over here, we're gonna say you wear glasses versus no glasses, okay? All right, I'm gonna just make up some numbers here. 15, 90. Oh, wait, these numbers are too small. Oh, no, it's fine. Okay, we're fine. Okay, so we'll do 7, 56, 8, 6. No. Why is this not working? Oh, I multiplied wrong. Okay, sorry. I take it back. Okay, it should be 7, 42, 48, 49, and what is this? 56. Okay, so these are the numbers I want to use. Okay, and so we just want to know, okay, to check if glasses and left-handedness are independent, we will check is the probability of A given B equal to the probability of A? All right? And if so, they're independent. Okay, so we just arbitrarily, we're going to call this A. We'll call left-handed A, which means not left-handed will be not A. And then over here, glasses will be B, and not glasses will be not B. Okay? So over here, it's going to be probability of left-handed given glasses. Is that equal to the probability of left-handedness? Okay? This is what we want to know. Okay, so what is the probability of left-handed given glasses? So we would say 7 out of 49, and we get 1 out of 7 here, right? Is that okay on this side? And then probability of being left-handed, this would be what? 15 out of 105, which also simplifies to 1/7. In my head, it makes sense. Is this okay with you guys? All right, so we got 1/7 is equal to 1/7. Yes, indeed, they are equal. They are equal. So that means they are independent. Okay, and at this point in time, we're just going to say, they're equal. They are independent, okay? Or, they are not equal, they are not independent. Now, later on in the course, we will talk about deviations from what we might expect. So, for example, you know, I made up these numbers so our numbers came out perfectly, right? So here, what if we did a survey and we did with actual people, and instead of 7 out of 49 and 15 out of 105, let's say I got 8 out of 49 and 15 out of 105, okay? And in that case, those numbers would not be exactly equal, right? They would be just ever so slightly off, okay? And so at this point in time, we would say, oh, those numbers are different, so they are not independent. But I think kind of in our gut, we feel like, that doesn't quite feel right. So later on in our course, we will talk about a proportion test, a two-proportion test, where we're going to say, is 8 out of 49, which is just ever so slightly different from 1 out of 7, is that, there's this term, significantly different from 1 out of 7, okay? And I think when we do the statistics behind it, or the math behind it, we will find out that they are not significantly different. But that's later on in the course. Right now, we're just going to say, if we wanted to check for independence, we're going to be checking these two fractions, 1/7 versus 1/7. Yay, they are equal, independent. 1/7 is different from some other number, then they are not independent. Okay, so we're just going to leave it at that. Okay, and again, these labels were arbitrary. Okay, I could have just as easily done probability of B given A is this equal to, if they are independent, it should be equal to what? Probability of B, right? Okay, and in this case, this would be probability of glasses given left. Is that equal to probability of glasses overall? Okay, and this would be 7 out of 15. Is that equal to 49 out of 105? And indeed, 49 out of 105 simplifies to 7 out of 15. So, yes, they are equal. Okay, so, you know, even if you labeled which event was A and which event was B different from me, or if you switched them around, you would come to the same conclusion. Just make sure that you are comparing left given glasses versus left, probability of left, and not some other number, okay? So, you know, common mistakes are comparing, you know, A given B versus B given A or something like that. There's no rule that says those two things have any, you know, have to be equal or not equal to each other. Okay. All right, so here is a clicker question. Okay, and so recall what mutually exclusive events are and recall independent events, okay? So the question is this. If two events are independent, could these events also be mutually exclusive? Okay, and your answers are yes or no. Okay, so think about that, okay? If two events are independent, could these events also be mutually exclusive? So, I mean, I could just say like some arbitrary probability of A is 0.2 and the probability of B is 0.4. I don't know, it doesn't matter. Okay, we'll say 5 more seconds to get your clicks in. So just click something, A or B. Okay, and let's see how you guys did. Okay, and the correct answer is B. Okay, so let's think about this, right? So independent events what does that mean? It means the outcome of one has no influence on the other. Okay? What are mutually exclusive events? Mutually exclusive. It means if one event happens, the other is now what? The other is impossible, right? Okay, and so mutually exclusive, that means that the outcome of one does influence the other, and in that it makes the other event impossible. Okay, and so if events are mutually exclusive, they cannot be independent, and likewise, if two events are independent, they cannot be mutually exclusive. Okay. Does that make sense? Okay, I hope that makes sense. All right, we'll wrap it up right there for today. I guess that's it. Good luck as you guys study. I'll see you guys on Friday, and we'll go from there.